Welcome to another coding tutorial, and in today's video, I'm going to show you how to make this musical pendulum waves. What we're going to do today is that we're going to simulate what you see right here, which is a set of 15 pendulums that dance together to create this pretty mesmerizing pattern. Based on the video description, the length of the longest pendulum has been adjusted so that it executes 51 oscillations in 60 seconds, and the length of each successive shorter pendulum is carefully adjusted so that it executes one additional oscillation in this period. And because there are a total of 15 pendulums, the shortest one undergoes 65 oscillations in 60 seconds. This experiment and the video is done by Harvard, and it is based on a design published by Richard Berg, and I will link everything down below. But before we go into how to make a set of 15 pendulums, why don't we start with just one? A simple pendulum basically is a mass that is attached to a string, and it swings back and forth in an oscillating motion, which is also known as a simple harmonic motion, and it can be represented by the sine and the cosine function. Let's start by defining x and y in terms of sine and cosine functions. So let x to be equals to the length, which is the length of the string times sine of angle, and y equals to length times cosine of angle. You might be confused whether I switch these two equations where I set x to be equals to sine and y to be equals to cosine, but this is no mistake. It is because of the orientation that we're looking at the pendulum. The angle that we're looking at here is relative to the vertical axis, where x is now the opposite side and y is the adjacent side, which is opposite to what we usually do, where angle is relative to the x-axis. And that's why x now equals to length times sine of angle and y equals to length times cosine of angle. First, I want to translate the origin point to the middle point at the top of the sketch. So let's move it with divided by 2 and 0. And then I'm going to draw a line from 0, 0 and x and y. Oh, and then I need to also set the length. How about we set it to 150 and also angle at 0. And as you can see here, right, when angle equals to 0, we get a vertical line instead of a horizontal line in the other examples. And then now let's draw the mass using an ellipse function at x and y, and let's give it a size of 10 by 10. And now if we want to move the mass, all we need to do is that we need to change the angle here, and how about we just increment it up by 0.01. And then now the mass moves in a counterclockwise direction. But that is not the motion of a pendulum that we want. What we want is that we want it to move in a more realistic fashion, which is back and forth around a center point. And to get that movement, we need to understand a little bit of physics. So if you look here, at this point in time where the pendulum is at equilibrium, meaning that it's not moving at all, there are two acting forces on this mass. The first one is gravity, right? That is a force that is pulling the mass down. But the other force that is acting on this pendulum is actually the force called tension that is coming from the string. So without this tension force, actually this mass would just fall onto the ground. But because at equilibrium, these two forces cancel each other, and that's why the pendulum is not moving. But if, let's say, the angle is now at 45 degrees, that is actually not the case. As you can see here, there are still two forces that are acting on the pendulum. The first one is gravity, and then the second one is tension, right? But at angle equals to 45, these two forces do not cancel each other out completely anymore. If we were to break the forces down into x and y components, you can see that the y components actually cancel each other out, but the x component, there is a positive net force in the x direction that is pointing to the left side, and that is why the pendulum moves to the left. And let's say that angle now is equals to negative 45. There's also a net positive force in the x direction again that is pointing to the right side, and that is why the pendulum moves to the right. And that's how the pendulum swings back and forth in this oscillating motion. But in the real world, actually there's another force called friction, and it will eventually cancel out this force in the x direction. But because we're in the virtual world, we can assume that friction equals to 0, and that is why our pendulum will swing forever. Now let's calculate what is this force in the x direction, and we can use the equation F equals to ma. And based on this diagram, F of x is equals to negative m times gravity times sine of angle. And it is negative because the positive x direction is to the right and negative is to the left. Even though we have calculated what is the force in the x direction, we're not done yet, because if you look here, what we're trying to figure out is what should be the change in the angle here such that we'll get a realistic motion of a pendulum swinging back and forth. So there are two equations that we need. First, we need to have actually two additional variables. The first one is the angle velocity, which is the change in the angle. And the second one is the angle acceleration, which is the change in the angle velocity. So let's actually define those two variables first. So let's set angle V to be equal to 0 and angle A to be equal to 0. Let's start with 0. And then what we're going to do is we're going to set two equations. So this angle is going to change based on the angle velocity. And then the angle velocity is going to be changed based on the angle acceleration. But then now what we need is to figure out what is this equation for the angle acceleration. First, let's look at this image here. The distance traveled by a pendulum can be described by this arc length. Let's call that S. The equation for an arc length is S equals to L, which is the length of the string, times the angle. But we don't just want to solve for the angle, we want to solve for angle acceleration, right, or angle A. And we can do that using this thing called derivative. So first, let's go one step. So to get the velocity, we can do velocity equals to L times angle V. And then to get the acceleration or the angle acceleration, we can do another derivative. So acceleration is the change in velocity, and that is equals to L times angle A. And then now we can solve for angle A. So angle A equals to acceleration divided by L. And then you remember the force in the x direction that we calculated earlier using the equation F equals to ma. And then now we can replace this acceleration variable with the A that we calculated earlier. And so now angle A equals to negative G divided by L times sine of angle. And that is the equation we're going to put in our code. And so angle A now equals to negative gravity, right, divided by the length times sine of angle. And we also need to set what gravity is, so let's set that. So in the real world, gravity equals to 9.8 meter per second square. But because we're doing this in the virtual world, we can essentially set it to be equals to anything. So I'm just going to set it equals to 1. And then we can click run. All right, and then now our pendulum is moving back and forth in a pretty realistic manner. So how about if I were to set gravity to 10? So basically it just moves a bit faster, right? All right, so now that we have one pendulum done, let's go and make a class. So come to this arrow here, click the plus sign, click create file. I'm going to call this file pendulum.js. Before we start writing a class, let's go to index.html. Come to this line of code here, copy and paste, change the name here to the name of your new file, and then this is how you integrate a new JavaScript file into your program. Let's go back to pendulum.js, start with the word class. I'm going to call this class pendulum. All right, so inside the constructor function, what do we need? If we go back here, basically we want all of this, right? We'll set gravity as a global variable, but all of these will be part of our constructor function. So we're not going to set the length as 200, so I'm going to actually set it as a parameter here. But for the angle variables, we can set it as these. And then the second method that I want to write is update, and that is going to be the equation that we calculate all of this. All right, so this dot angle A will be equals to gravity, which is global, this dot length, this dot angle. All right, so put all the this dot on all of this. And then here is where we set the X and Y location, right? All right, and then now we just need to display the pendulum. So let's go back. We're going to put this translate here. right? We want to translate it one time, and then we can just display the line and the mass. All right, let's try to create just one pendulum. So how about we call it P, and P is going to be a new pendulum. And then we need to put in the length in here. So let's just put in 150. Then we need to call the method. So update and display. All right, let's bring the gravity back to 1. Okay. All right, so now we're ready to create 15 pendulums. But first, let's try to be on the same page on key few terms. The first one is period, and period is how long it takes for a pendulum to complete one oscillation or one cycle, and it has a unit of time. The second one is frequency, which is actually the opposite of period. It is the number of oscillations that can be completed in that same unit of time. So let's say that the frequency equals to 4, so it can complete 4 oscillations in 1 second, right? So what is the period? The period is 1 over frequency, so 1 over 4. So the period is 1/4 or 0.25 second. And if you remember at the beginning of the video, what we're trying to do is that we're trying to simulate these set of 15 pendulums that start at the same time and then kind of move at a pretty random manner and then synchronize back at a given point in time. And that given point in time actually is after 51 oscillations. And that is because the longest pendulum oscillates at 51 oscillations per a given amount of time. And what we need to do to be able to do this simulation is that we need to calculate the length for the 15 pendulums such that it would synchronize back. And we can do that using first the equation of a period. So a period for a pendulum equals to 2 pi times square root of L, which is the length, divided by gravity. And then we just rearrange it to find L, or the length, which is equals to gravity times period divided by 2 pi square, and period is just 1 over frequency. Let's start by changing this variable from P to an array called pendulums. Then we also want to set a number equals to 15. And then, and then that's it. So inside setup, we want to create a for loop that goes from I equals to 0 to I less than num, I plus plus, and then we want to create 15 pendulum objects, right? So pendulums of I will be equals to new pendulum, but not of 150, right? We want to calculate what this length is going to be. Length, which equals to gravity times period divided by 2 pi square, right? And we can get the square calculation using the function pow. So we want to put in the first argument as the base, and then the second argument is the power that we want to raise it to. So 2, and then now we need to set what period is. So period would be equals to 1 divided by frequency, right? I'm actually going to also set a variable called frequency 0, which is the frequency of the longest one, which is 51, right? And so now what we want here is 1 over frequency of 0 plus I, right? Because each subsequent one will be incremented by 1, right? So it will go from 51 to 65. All right, and now we have to call the update and the display method on all of the pendulums objects. So pendulums of I and pendulums of I. Oh, you see that? Why is it all the way up top? So let's actually print length here. They're very, very small numbers, right? And what we can do to get a reasonable number for the length, right? We just multiply it by, how about we call it a length multiplier, and let's set it to, let's see, 1, 2, 3, 4, 5, 6, 7. Let's do 7. So 1, 2, 3, 4, 5, 6, 7. And then we just multiply this length by this variable length, no, not here, times length multiplier. Let's try that. Okay, that's not bad. We can make it a little bit bigger. All right, I'm actually going to also increase the width here, and then I'm going to delete this. All right, so now we get our 15 pendulums. Before we move forward to the sound part, what I want to do is I want to make it pretty. First, I want to create another method called collision. And this is basically is going to tell me when the pendulum actually is at equilibrium or at x equals to 0. So we're going to write a conditional statement that says if this dot x is less than or equals to, let's do 10, and this dot x is greater or equals to 10. And the reason that I put 10 here is to give it a buffer such that within the range of between -10 and 10, actually this has to be negative. -10 and 10, that is when I want it to return true. So that's what I want to write here. Return true, and then else return false. Okay, and then inside update, I want to call this method. And to call a method inside a class, all you need to do is just do this dot and then the name of the method, right? So if this collision returns true, what I want to do is I want to set the color to white. And else I want to set this to just black. And how about we set this to be black originally. Okay, let's click run. Ooh, this has to be greater than and this has to be less than. Oh, I forgot to put stroke color. Let's set it to this.c. All right, you see that? The ones that are in the middle turns white. Okay, so let's change the colors a little bit. So I'm going to set an array of colors to be these nice blue set of colors. And then now inside here, what I'm going to do is I'm going to set color this.c as a parameter c here. And then so it will turn white when it collides, and then it will set back to, so I'm going to actually call this NC, and this NC, which is new color, is going to set back to the original color C that I set here, and this will be NC as well. And then if we go back to sketch.js, then we need to put in an argument for color here. And I want to actually put in I here, but we have what, 15 pendulums, but we only have 4 numbers, so we need it to loop around. So we can do that using an expression called modulus, which is this percentage sign. So we would do I mod and then the length of this array here. The modulus operator, what it does is that it returns the remainder between the division between these two numbers. So I and c.length. c.length is 4, right? 1, 2, 3, 4. And then I goes from 0 to 15. So between 0 and 3, it will return the value between 0 and 3, right? But once it hits 4, so 4 divided by 4 has no remainder, so it will return 0. So 5 divided by 4 will return 1, and so on. So it will loop through this array perfectly. Now let's try that. All right. I want to also set fill color here to be this .nc. Okay, and then the last thing is I want to change the size. So let's set size, this .size equals to size. I want it to be a little bit different, each one of the pendulums, and I want the closer one to us to be slightly bigger. So I'm going to actually set s to be equals to, so I want the smallest one to be equals to 10. Then I'm going to add it to I times, how about 0.5. Then I'm going to set that as my size. the size doesn't change. Oh, I think I forgot to actually use this size variable here. So we want to replace it here, right? This dot size and this dot size. Let's try that. All right. So you can see that the closest one to us is the biggest, right? Maybe that's a little bit too big. What if we change it to like 5? All right, I think that looks better. All right, that looks pretty cool already. All right, so now we're ready to add some sound. So actually I have a few tutorials that show you how to upload and use MP3 files in your sketch to create some interesting tunes. But in this tutorial, we're going to take a different approach. We're going to use a P5 class called P5 Oscillator, which is part of the P5 sound library. And we're only going to scratch the surface in this video here, because there's actually so much that you can do within the P5 sound library, and I hope to make more videos on that later. Let's talk through how we're going to approach this. Sound can be measured in terms of frequency and amplitude. And frequency is the pitch, which is how high or how low the note is that you're hearing, and then amplitude is the volume. And each of the notes that you hear actually has its own frequency. For example, the note A actually has a frequency of 440 hertz. The notes that I want to use in this example is a C major chord, which is C, E, and G from 5 different octaves, so that makes 15 notes. And each of the notes actually are assigned by a specific number, and these numbers are called MIDI notes. And as you can see here, the MIDI notes have its own frequency. So let's look at this middle C here, which has a MIDI note of 60. It has a frequency of 261.625 hertz, right? So let's click play. So that's a middle C. And then if you look at this next one with a MIDI note of 72 and a frequency of 523.25, it is just a C in one octave above, right? C in the middle of treble clef. So let's play this. It's just a higher C, and it has a different frequency and also a different MIDI note. So what we're going to do is that it's kind of hard for us to get all of these frequencies. So we're going to get the MIDI note for the C major chord that I want, and then we're going to convert it from MIDI to frequency. To use the oscillator class, we're going to start by creating a variable called OSC. And then inside setup, I'm going to set OSC to a new p5.oscillator object. And then we want to start the oscillator, and we can do that using a function called start. Click run. It kind of plays a tune already, right? And then what we want to do is that how about we set a frequency, so we can just do OSC.freq, and then we just put in the frequency that we want. So let's say that we put in 440, right? So that is an A note. I guess that's the default note because it's the same sound that we heard initially. And then what we want to do is that we want to set an amplitude, which ranges between 0 and 1. So if I put in 0 here, you don't hear anything. If I put in 1, all right. Then if I write a conditional statement that says if mouse is pressed, which returns true when I press my mouse, then I want to set the amplitude to 1. And then else, I want to set the amplitude to 0. So that's how I'm going to turn on and off this oscillator. And I want to start it at 0. Click run. I press my mouse. I release my mouse. Press my mouse. Release my mouse. Do you hear that? There's like this sound at the end and the beginning. And that is because it goes to 1 and 0 amplitude too abruptly. And what we can do with this is that we can provide a second argument that will help it ramps up and ramps down the volume. So let's say I put in 0.05 for both. You see it's smoother now. And the last thing I want to show you is that I want to show you how to convert from the MIDI note to a frequency specific to that note, right? So let's say that we have a MIDI note at 60, right? That's the C, the middle C. We can just use the function called MIDI to freq, and then we provide the note. All right. So that's exactly what we're gonna do. So we want the pendulum to play a note when it collides or when it hits the middle point, right? First, we're going to create another parameter called OSC. Then let's set OSC to be a new oscillator, right? And then we can just copy this. Then we need to make sure that we put in this dot for all of this. And instead of MIDI note here, I'm going to put in this dot note, and we're going to set this dot note as another parameter. Actually, we don't need OSC here. It will be just note. Okay, and then inside here, right, when we call this dot collision, when it hits, we want this dot OSC dot amplitude to be 1, right? And then we want to also provide this second argument to help it slowly ramps up. And then do the same thing, set it to 0 for this one. Okay. Now, if we go back to sketch.js, we need to create an array of MIDI notes, right? And as I told you earlier, I want to have a C major chord from 5 different octaves. And then inside here, we need to provide MIDI notes of I. And how about we just put in mod of MIDI notes dot length here, just in case you want to change the MIDI notes here and it's not of the same length as the number of pendulums. It will not give you any errors. And I think we're ready. Okay. Oops. Oscillator is not defined. Oh, I forgot the word p5 dot because it's part of the p5 library. Okay, ready? And ta-da! Here is your musical pendulum waves. I hope they enjoyed this tutorial as it combines many different concepts, from oscillation to forces to movement to sound, which outputs something very interesting. So give this one a try.